my name is Danielle Rodriguez, and I was given the drug Topamax for my molecular portfolio project. And the generic name for this drug is Topiramate, and the chemical name is right here, as you can see. So the first thing we want to know about this drug is, what is this drug used for? And this drug is used to treat or prevent seizures, treat migraine headaches. The second question is when you should not take the drug. So you shouldn't take this drug if you're allergic or hypersensitive to the drug. You shouldn't take it in combination with alcohol, and you shouldn't take it if you have metabolic acidosis. So we also want to know, what are some significant interactions with other drugs? This drug does not interact well with other anti-seizure medications because it slows brain activity, and in combination with other drugs that do the same thing, it could be really harmful. Opioid pain relievers and alcohol do the same thing. They act as a sedative and slow brain activity, so it could lead you to be further impaired. And also, we shouldn't take this in combination with oral birth control because it can make the birth control not effective. What is something interesting about the drug? So this drug is also prescribed for things like weight loss, bipolar disorder, and alcohol disorder, even though it's not proven to be effective for these things. Here you can see the skeletal line structure for the drug Topamax or Topiramate. So now I'm going to draw the Lewis structure for my drug Topamax, and I'm going to draw a couple carbons with hydrogens coming off them. So each of these have 3 hydrogens, and they meet on one single carbon over here. And then we've got 2 bonds coming off that carbon, and they both go to oxygen. And these oxygens both go to a couple carbons, and then they kind of meet right there. We need to go back and complete this octet, so we're going to give this 2 lone pairs on each of those oxygens. Now I'm going to put this hydrogen coming up because this is important to its shape or the geometry of this molecule. And so this one has a carbon coming down here, and this one's attached to a carbon too, and this one's attached to an oxygen, and we have a carbon here, and again they kind of meet at the middle. Now I'm going to draw this one, this hydrogen, coming off like that because again it's important to its geometry and its shape. Let's see, carbon, and then an oxygen, and then a carbon. And then I'm going to go back in and I'm going to fill in some of these, so we need to complete these octets. So I'm going to put hydrogens here. This oxygen is going to have 2 lone pairs, and then we're going to come down to these. We're going to give the oxygens both are going to have their lone pairs. And then this carbon has 2 bonds coming off of it. Both of those are linked to carbons, and that's where these carbons kind of finish off. And we're going to give them hydrogens to complete that octet. Oops. Okay, so then over here, this carbon only has 3 bonds. We're going to add one. But this kind of changes the shape. It's kind of pulled out over here, and it's attached to a carbon, which is then attached to an oxygen, which is then attached to a sulfur, which is then attached to a nitrogen. And this is kind of where this one finishes off. We have 2 hydrogens coming over here, but we need to complete these. So I want to give this carbon all of its bonds. So we have 2 hydrogens. This is going to have 2 lone pairs. Now the sulfur is bonded to 2 oxygen, but it's double bonded to 2 oxygen. And in order to complete those oxygens, we just give them 2 lone pairs. And one more thing is this nitrogen over here likes 5 attachments. So we need to give it 1 more lone pair. And this is the Lewis structure for Topamax. Just going to circle the geometry of these. So tetrahedral I'm going to do in blue, and all of these are tetrahedral. These carbons, because they have 4 bonds coming off of them, tetrahedral, and this one as well. And we're going to come over here and do our carbons. These are all tetrahedral. And then the next one we're going to do is trigonal pyramidal, and I'm going to do that one in a sort of pink color. And so that one, the only one we have in that one is over here. And this one's a little bit of a lighter pink, sorry for the colors, but this one is bent, so you can see the ones that have a lot of the lone pairs over here are bent. This is bent, and this is bent. And I believe that's it. So that is the geometry for each of the molecules. Each of the elements of this molecule. I was able to get the molecular formula by adding up how many carbons, hydrogens, nitrogens, oxygen, and sulfur atoms were in my molecule. Once I found out how many carbon atoms we had, I multiplied that by the atomic mass, and that gave me 144.132. I continued that with each of the atoms. Once I was done adding up each individual one, multiplying each individual one. Then I added up all of the sums, which gave me 339.364, and that is the grams per mole. So it's the mass per mole. And then I went ahead and rounded that to the hundredth, which gave me 339.6 grams per mole. Here we were given the task to show how this molecule could form hydrogen bonds with water. So you can see that anytime there's an oxygen bonding to the larger molecule, to a hydrogen, then that's going to be a hydrogen acceptor. Anytime the water molecule has a hydrogen that's bonding to one of the oxygens on the larger molecule or fluorine, then that is a hydrogen donor. So basically the water molecule is donating a hydrogen, and when the oxygen is receiving a hydrogen from the larger molecule, that is a hydrogen acceptor. Here I've drawn my molecule, Topamax, and this demonstrates how the molecule forms hydrogen bonds with water. So I color-coded them so you can see the blue ones are hydrogen acceptors, and this is where the oxygen in water is bonding with the hydrogen from the molecule. And in the green ones, we have the hydrogens from water bonding with oxygens or nitrogen from the molecule. So these are my polarity and solubility predictions. I went ahead and drew out the dipole moments, and you can see that oxygen is more electronegative than carbon, so there's definitely going to be a bit of a pull in these directions where all of the oxygens are. However, on the outside of the molecule, these are nonpolar, and these are usually the things that interact with like other atoms or molecules first. Over here, we do have a pull towards the nitrogen over here. So you can see that nitrogen is more electronegative. So the hydrogens and sulfur both pull up and pull towards that nitrogen. These oxygens on the sulfur are going to pull pretty evenly. And we'll probably get more of a pull towards the oxygen and sulfur or sulfur and nitrogen. So this area is going to be a little bit more polar, but overall I would say that most of this molecule is nonpolar because we don't have much of poles here because of the carbons and hydrogens here. And then these are kind of closely related on the periodic table, so they're not very polar. They don't have too much of a pull to them. So the question is this water soluble? I did a little research and it says, I found that no, Topamax is more soluble in alkaline solutions, having a pH of 9 to 10. Topamax is a mostly nonpolar molecule, and nonpolar regions of the molecule are not water soluble. Finally, we are asked to prepare solution calculations, and in our first question, we have to prepare 50 milliliters of 2.30 times 10 to the negative second molarity solution of our drug, and we're asked to prepare this solution from the pure drug and deionized water. So in order to do that, we need to find out how many grams or moles of the drug that we have. So first we have to find a a formula to use, and I went ahead and used molarity equals moles over liters, but in order to solve for moles, I just went ahead and did the algebra real quick. So what we're actually plugging in is liters times molarity equals moles. So you can see I, on the right hand side, went ahead and converted milliliters into liters, because in order to do this it has to be into liters, and I converted the 2.30 times 10 to the negative 2 molarity into the decimal. So when I plugged it in, I got that moles equals 0.00115, and in order to complete this, I needed to do the conversion factor, and I already found out how many grams of my drug per mole. So I went ahead and multiplied the number of moles I got by the grams per mole, and I got 0.39 grams of Topamax. So in order to perform number one, I would need to weigh out 0.39 grams of Topamax, and I would need to put it in a volumetric cylinder or flask. And once I've done that, then I would go ahead and fill the flask up to the 50 milliliter mark, and that should create my solution for me. Now, number two asks me to calculate how many milligrams of the drug are contained in 2 milliliters of a 3% solution of my drug. So again, I found the formula. We want to do mass over volume equals mass of solute over volume of solution times 100, and then again I put but I just kind of moved everything around so that I could actually just solve for mass of solute in grams. So once I plugged in the 3% and times 2.0 milliliters, and then I divided by 100, my answer I got was 0.06 grams. However, they're asking for it in milligrams, so I went ahead and converted 0.06 grams, and my answer for number two is 60 milligrams.